Module 7. Unit 14. Weather patterns and severe storms. Weather patterns and severe storms are compelling examples of the power and complexity of Earth's atmospheric systems. These phenomena are shaped by interactions between air masses, atmospheric pressure, and temperature differences, which drive the creation and evolution of weather fronts, cyclones, thunderstorms, tornadoes, and hurricanes. Understanding the underlying processes not only explains the behavior of storms, but also highlights the interconnectedness of atmospheric elements. Air masses are large bodies of air with relatively uniform temperature and moisture content. They originate in specific regions such as polar areas, tropical oceans, or continental interiors, and are classified based on their source regions. For example, an air mass that forms over the warm waters of the Gulf of Mexico is classified as maritime tropical, MT, characterized by warm, moist conditions. This type of air mass supplies much of the moisture for precipitation in central and eastern parts of the United States. In the Midwest, particularly in areas like Missouri, the dominant air masses are MT and continental polar, CP, which bring contrasting weather patterns due to their differing characteristics. The interaction of these air masses often leads to dynamic weather events, including thunderstorms, snowstorms, and other forms of severe weather. The boundaries between air masses, known as fronts, are key to understanding weather patterns. A warm front forms when a warm air mass advances over cooler air, producing gradual lifting and leading to cloud formation. Observers witnessing the approach of a warm front might first see cirrus clouds, followed by cirrostratus and altostratus clouds. This sequence indicates the gradual thickening of clouds as the warm air rises and cools, eventually resulting in steady precipitation. In contrast, cold fronts occur when a cold air mass advances and pushes warmer air upward rapidly, often bringing sudden weather changes such as thunderstorms and heavy rain. A wind shift from the south or southwest to the northwest often accompanies the passage of a cold front, signaling the arrival of cooler, drier air. When a fast-moving cold front overtakes a warm front, an occluded front forms. This occurs when the colder air completely displaces the warm air aloft, resulting in a mix of weather conditions including rain, snow, or sleet. For example, in St. Louis, Missouri, a winter day might begin with snow due to a passing cold front, transition to rain as a warm front moves in, and later revert to sleet and freezing rain as another cold front arrives. This sequence occurs because the warm air between two cold air masses is lifted, causing precipitation to change as temperatures fluctuate. The middle latitude cyclone is a classic example of weather systems shaped by air mass interactions. These cyclones, which often develop along fronts, feature a rotating system of low pressure. As the center of a mature wave cyclone passes, barometric pressure rises, signaling the movement of the system and a shift in weather conditions. The combination of warm and cold air masses in these systems generates diverse weather, from clear skies in the high-pressure regions to stormy conditions near the low-pressure center. Severe storms such as thunderstorms, tornadoes, and hurricanes demonstrate the immense energy contained within the atmosphere. Thunderstorms form when warm, moist air rises rapidly, creating towering cumulonimbus clouds. These storms are often accompanied by heavy rain, lightning, and strong winds. Tornadoes, which are associated with severe thunderstorms, occur when rapidly rising warm air creates an area of very low pressure. Surrounding air swirls inward at high speeds, forming a rotating column of air that touches the ground. Tornadoes are most common in the Midwest and Great Plains of the United States, particularly in spring, when warm, moist air from the Gulf of Mexico interacts with cooler, drier air from the north. Hurricanes, another type of severe storm, are tropical cyclones that develop over warm ocean waters. Their formation begins with a tropical depression, where winds do not exceed 61 kilometers, 38 miles per hour. As the system intensifies, it becomes a tropical storm, with winds between 61 and 119 kilometers, 38 to 74 miles per hour. To be classified as a hurricane, a storm must have wind speeds exceeding 119 kilometers, 74 miles per hour, and exhibit rotary cyclonic circulation. Hurricanes form between latitudes 5 degrees and 20 degrees in all tropical waters except the South Atlantic and eastern South Pacific. They derive their energy from condensing water vapor and require warm ocean waters to sustain their strength. The center of a hurricane, known as the eye, is an area of very low pressure surrounded by the storm's most intense winds and rain. Hurricanes weaken when they move over cooler ocean water, land, or encounter unfavorable atmospheric conditions, as these factors disrupt the energy supply necessary for their growth. For instance, as a hurricane moves over land, the absence of warm water reduces the evaporation and condensation processes that fuel the storm. Similarly, cooler water or changes in large-scale atmospheric flow can diminish the intensity of a hurricane. The devastating power of hurricanes highlights the importance of monitoring and understanding these storms. Scientists have speculated that increased carbon dioxide emissions and associated global warming may lead to more active hurricane seasons. Warmer ocean waters, a key ingredient for hurricane formation, could increase the frequency and intensity of these storms, posing significant risks to coastal communities worldwide. Weather patterns are further influenced by global and regional atmospheric dynamics. For example, the Intertropical Convergence Zone, ITCZ, is a region near the equator where trade winds converge, causing air to rise and leading to heavy rainfall. Similarly, the jet stream, a fast-moving ribbon of air in the upper atmosphere, acts as a boundary between cold polar air and warmer tropical air. Its position and strength influence the development and movement of cyclones and anticyclones in mid-latitude regions. Understanding weather patterns also involves reading and interpreting weather maps. These maps display information such as pressure systems, fronts, and precipitation, providing a visual representation of atmospheric conditions. For example, areas of low pressure are marked with an L, indicating regions of rising air and potential stormy weather. In contrast, areas of high pressure are marked with an H, signifying descending air and more stable conditions. Fronts are depicted as lines with symbols indicating their type, triangles for cold fronts, semicircles for warm fronts, and combinations of both for occluded fronts. By analyzing these maps, meteorologists can forecast weather changes and provide crucial information to the public. Unit 15. Weather patterns and severe storms. Earth's climate system is a dynamic interplay of atmospheric, oceanic, and terrestrial processes, shaping the diverse climates experienced around the globe. Understanding these systems is critical, particularly as the effects of global climate change become increasingly evident. The Köppen system of climate classification, a foundational tool in climatology, categorizes climates into 5 principal groups based on temperature, precipitation, and vegetation. This classification provides a framework for analyzing the characteristics of different regions and assessing the impacts of climate variability and global warming. The 2 most critical elements in describing climate are temperature and precipitation, which directly influence the habitability and ecological characteristics of an area. Desert climates, for instance, are defined by their high temperatures and minimal precipitation, making them warm and dry. For individuals who suffer from bronchial conditions exacerbated by humidity, moving to a desert climate could provide relief. These arid regions, often found in subtropical zones, are shaped by global circulation patterns that limit moisture availability. Dry climates, including deserts and steppes, cover approximately 30% of Earth's land area, making them one of the most widespread climate zones. These regions are distributed primarily along certain latitudes due to the influence of global atmospheric circulation. For example, deserts often align with the descending air of the subtropical high-pressure belts, where dry, stable conditions dominate. Steppe climates, which are semi-arid and serve as transitional zones between deserts and more humid regions, share similar latitude distributions, but experience slightly higher precipitation. The Köppen classification also identifies marine West Coast climates, characterized by mild temperatures and abundant precipitation throughout the year. These climates are situated on the western windward sides of continents between 40 and 65 degrees latitude in both hemispheres. Europe contains the largest area of marine West Coast climate, supported by prevailing westerly winds and proximity to the Atlantic Ocean. The combination of oceanic influence and frequent precipitation makes this climate type ideal for supporting dense vegetation and agricultural productivity. Highland climates, found in mountainous regions, are another unique category within the Köppen system. Compared to lower elevations, highland climates are generally cooler and wetter due to altitude's effect on temperature and precipitation. These areas are often biodiversity hotspots as their varied microclimates support a wide range of plant and animal species. They also serve as critical water sources, with precipitation feeding rivers and reservoirs that sustain communities downstream. Global climate patterns are deeply intertwined with natural processes and human activities. The combustion of fossil fuels, such as coal and oil, has significantly increased atmospheric carbon dioxide levels, contributing to the greenhouse effect and global warming. Reducing fossil fuel use and transitioning to renewable energy sources, such as solar power, could help mitigate these effects. The Intergovernmental Panel on Climate Change, IPCC, strongly supports renewable energy development as a means to combat climate change and promote sustainability. One argument frequently posed against the reality of global warming is based on individual years with cooler temperatures. For example, after a series of warmer than average years, a single cooler year in the United States might lead some to claim that global warming has ceased. However, this argument is flawed. Climate trends must be evaluated over extended periods, as short-term variability is influenced by numerous factors, such as El Niño and La Niña events. The year 1998, for instance, was exceptionally warm due to a strong El Niño, which caused warmer ocean temperatures in the Pacific. While this anomaly does not negate the broader trend of global warming, it highlights the need to consider long-term patterns rather than isolated events. Global warming disproportionately affects certain regions, particularly those already vulnerable to climate extremes. Alaska, for instance, experiences dramatic changes as rising temperatures melt permafrost and reduce sea ice coverage. These changes disrupt ecosystems, threaten wildlife, and challenge indigenous communities that rely on stable environmental conditions for subsistence. Similarly, small island nations face existential risks from rising sea levels and more intense tropical storms fueled by warmer ocean waters. The relationship between global precipitation and pressure systems further illustrates the interconnectedness of Earth's climate. The Intertropical Convergence Zone, ITCZ, where trade winds converge near the equator, is a region of intense precipitation driven by rising warm air. Conversely, subtropical high-pressure zones are associated with dry conditions, creating deserts and semi-arid regions. These global circulation patterns shape the distribution of wet and dry climates, emphasizing the role of atmospheric dynamics in defining regional characteristics. Climate classification systems also shed light on the societal and ecological implications of climate change. For example, warmer and drier conditions in regions like the American West exacerbate droughts, increasing the frequency and severity of wildfires. These changes affect water resources, agriculture, and biodiversity, challenging communities to adapt to evolving environmental conditions. Renewable energy initiatives, reforestation projects, and sustainable water management practices can help mitigate some of these impacts and support resilience in the face of climate change. Despite significant progress in understanding climate systems, misinformation and skepticism about global warming persist. Arguments that claim global warming stopped after a particular year, such as 1998, often ignore the complexities of climate science. Climate is influenced by long-term trends, while weather varies annually due to natural oscillations like El Niño and La Niña. The overall trend, supported by decades of data, shows a consistent increase in global temperatures. Addressing these misconceptions is crucial for fostering informed discussions and driving effective action. Nitrogen, the most abundant gas in Earth's atmosphere, comprises approximately 78% of the air we breathe. While not a greenhouse gas, it plays a vital role in supporting life by contributing to the nitrogen cycle, which is essential for plant growth. However, it is carbon dioxide, constituting a much smaller percentage of the atmosphere, that has garnered attention due to its role in global warming. Human activities, particularly the burning of fossil fuels, have increased atmospheric carbon dioxide concentrations, amplifying the greenhouse effect and raising global temperatures. Climate change is not only a scientific issue, but also a moral and ethical challenge. Reducing carbon emissions requires collective action and a commitment to sustainable practices. Investments in renewable energy, such as solar and wind power, can reduce dependence on fossil fuels and limit the release of greenhouse gases. Additionally, individual actions, such as conserving energy, reducing waste, and supporting policies that address climate change, can contribute to global efforts. The study of world climates and global climate change reveals the intricate interplay of natural processes and human activities shaping Earth's environment. The Köppen system of climate classification provides a framework for understanding the diverse climates that define our planet, from deserts and marine west coasts to highland regions and tropical zones. As global warming accelerates, its impacts are felt disproportionately across regions, challenging societies to adapt and mitigate its effects. By addressing the root causes of climate change and embracing sustainable solutions, humanity can work toward a more stable and resilient future for generations to come.